In this video, we're going to look at the least squares solution for AX equals B. So consider the case where B is not in the range of A or not in the column space of A, which means that we have an inconsistent system. And also recall that the orthogonal complement of the column space of A is the null space of A transpose. So if B is not in the column of A, then there exists some AX hat in the column space of A, and that's what we're interested in. What's the best solution possible for this system which is inconsistent and doesn't have a solution? And we'll call that solution AX hat. Right? So AX hat is in the column space of A, and we really want then B minus AX hat will give you another vector which AX hat plus B minus AX hat gets you back to B, and B minus AX hat must be an element of the null space of A transpose if you want AX hat to be as close as possible to B. So if B minus AX hat is known to the null space of A transpose, then A transpose times B minus AX hat is equal to the 0 vector, and this allows me to generate what are called our normal equations in least squares. So for any matrix A transpose AX hat equals A transpose B is the normal equations for that system. And so if the columns A are linearly and the solution to that is called the least squares solution. Now it's possible that A transpose AX, A transpose B has more than one solution, right? You could have a multi-dimensional null space. So when the columns of A are linearly independent, then A transpose A is an invertible matrix and there is a unique least squares solution. And in that case, the distance B of B minus AX hat is called the least squares error. So let's look at an example here. We want to find the least squares solution to x plus 1 equals 3, 2x plus 1 plus x sub 2 is equal to 1, and x sub 1 plus x sub 2 is equal to 1. So this system has no solution. It's inconsistent. It's an overdetermined system ripe for least squares. So I've go ahead and pulled out A and pulled out B. So the way I go about doing this, I generate the normal equations. So A transpose AX hat and A transpose B. Here's A transpose. Here's A. Here's A transpose. There's B. So I multiply those together. Notice A transpose A is going to get you a n by n, not an m by m matrix. I'm going to write that in here. Okay? And A transpose B will get you a column vector that is also n-dimensional. So we now have a system of equations. Notice that 6 times 3 is 18 minus 16 is not equal to 0, so this has a unique solution. So I'm going to use what I know about how to find the inverse of a 2 by 2 matrix, and I'm going to solve this and get my unique least squares solution, which is minus 1, column vector minus 1, 3. Notice I could also solve this using row reductions, and if A transpose A was not, if A didn't have linearly independent columns, then that's what I would have to do, because A transpose A would be not invertible. So our least squares solution, I'm going to kind of write it. Our least squares solution now that's the least squares solution. If you want to actually find the vector that's in the column space of A, right? So remember our drawing. If I want to actually find those, then I have to do A times x hat. So I do A times x hat. Here is the vector that's actually in the column space of A. You might want to think about that as the projection of B into the column space of A. So now I can find the least squares error, which is the magnitude of B minus AX hat, which is the magnitude of 311 minus 212, which is, I just wrote this as a row here. That's a notation that we use when we want to save some space. It still means column vector because I use parentheses. So that's what? The square root of 1 squared plus 0 squared plus minus 1 squared, which is 2. So the length of that mean least squares error amount is root 2.